In this video, we're going to discuss the atomic radii. So the size of an atom is usually reported as that atom's atomic radius. Of course, atomic radius is actually a little tricky to measure because atoms are not solid spheres. As we know, according to the quantum mechanical model, we don't know exactly where the electron is, so we only know with a certain probability. And so that makes it more difficult to measure how the atomic radius of an atom. So to do that, in order to measure the atomic radius, we measure what is called the covalent radius. The covalent radius is defined as 1/2 the distance between the nuclei of two identical atoms when bonded by a covalent bond. So let's look at a couple of examples. Let's say here we had fluorine, or F2. We had two fluorine atoms bonded together. We can experimentally measure the distance between the two nuclei. Here you can see it's 128 picometers. Well, this gives us a pretty good estimate of the atomic diameter. So the atomic radius would be 1/2 of that distance. So the atomic radius for fluorine would be about 64 picometers. And as you can see, atomic radii are very, very small, so they're generally measured in picometers. So here we have Cl2. We can measure the distance between the two nuclei, and 1/2 of that would give us an estimate of the atomic radius, so the distance from the radius to the outermost orbital. Now, another thing that's very important to appreciate is not just how it's measured, but the periodic trends that are related to atomic radii. Atomic radii tend to decrease as we move from left to right across a period. They tend to increase as we move down a group, and they increase when we start a new period. So if we look here at this periodic table, you can see, let's look at the n equals 2, the second period. You can see these numbers are the atomic radii, so you can see that the atomic radii tend to decrease as we move from left to right across a period. Now there's a few exceptions when we get into d orbitals, but for the main group elements that trend is pretty clear. So the atomic radii decreases as we move from left to right across a period. You can see as we move down a group, let's look at the group 1 here, the atomic radii get bigger. And if we start a new period, so let's say here we go from fluorine to sodium, the atomic radii increases and then it starts to decrease, and then we start a new period, it increases again. Now, the atomic radii as we move across, you may think that it should increase because we're adding protons and electrons as we move across, but it actually decreases. So how do we explain these periodic trends? How do we explain these three periodic trends? Let's take a moment and do that. So first of all, the size of an atom, or its atomic radius, is related to the atom's effective nuclear charge. So be sure you have a real good understanding of what effective nuclear charge is. So as we move across a period, if you recall, the effective nuclear charge for the atoms increases. Well, the outermost or valence shell electrons therefore experience a greater attractive force towards the nucleus. So as the effective nuclear charge increases from left to right across the periodic table or across a period, the valence electrons experience a greater effective nuclear charge, and this causes those electrons to be drawn closer to the nucleus, resulting in a smaller atomic radius. So even though we are adding electrons, they're added to the valence shell. Valence electrons provide less shielding. We are increasing the actual nuclear charge, and so those valence electrons and all the electrons, the core electrons as well, are drawn closer to the nucleus, resulting in smaller or decreasing atomic radii across a period. Well, what about down, as we go down a group, we said the atomic radii increase. Well, that's of course because as we go down a group, we're starting a new valence shell every time we go down a group. The new valence shell has higher energy and therefore larger and further from the nucleus. And as we add these new valence shells, it causes the atomic radii to increase. So here you can see a periodic table which has the valence electron configurations, and you can see as we go down a group, we we increase the number of the valence shell. So we go from sodium has a 3s1 valence configuration to potassium with a 4s1, etc. So as you go down any group, the valence shell gets larger further from the nucleus, causing the atomic radius to get larger. What about when we start a new period? We said the atomic radius increases. Well, this is because the valence shell, we start a new period, a new valence shell is started. And so much as we said before, when we start a new valence shell, that shell is further from the nucleus, causing the atomic radius to increase. But it's also related to its effective nuclear charge. When we start a new period or add a new valence shell, there is a large reduction in that atom's effective nuclear charge, resulting in increased atomic radius. So let's illustrate this by looking at neon to sodium. When we go from neon to sodium, we're starting a new period. And here you can see neon's electron configuration. And the effective nuclear charge felt by these valence electrons is fairly large because there's very little shielding, only 2 core electrons, relative to its actual nuclear charge of 10. So these electrons are pulled very tightly towards the nucleus, resulting in a small atomic radius. However, when we go from neon to sodium, we only add 1 proton, but we start a new valence shell. This valence electron, this 3s electron, experiences a great increase in the amount of shielding, because now instead of just 2 core electrons, we have 2, 4, 6, 8, 10 core electrons. So this electron will experience a very large reduction in the effective nuclear charge, meaning that it's not going to be drawn as tightly to the nucleus. This results in an increase in atomic radius anytime we start a new period. So be sure you can explain these periodic trends for atomic radius, and be sure you can explain them correctly and completely in terms of effective nuclear charge.